Howdy, this experiment is designed to find out what the second stage precipitate might or might not be. It could be magnesium hydroxide that has just snuck through in the and somehow exists at pH less than 9. And so I've worked out that I can collect some of the magnesium hydroxide in the first precipitation, take the sample down to pH 1 and back up to 8.7 and should get the regular precipitate, and then take an equal sample size of that to the other and run both of them separately up to pH of 12. Now it's said that M-state material will be soluble at pH above 12, whereas magnesium hydroxide won't be, so let's find out. Now I'll add the Dead Sea salt and get that dissolving over the next 10 or 15 minutes. And meanwhile, let's have a look at some charts, and then we'll go straight towards the latter part of this experiment. This is a table of all the possible reactions I could find using Dead Sea salt precipitation. So it's a table of outcomes using sodium hydroxide, hydrochloric acid and water, which are the only inputs apart from the Dead Sea salt itself, and to try and identify what the isolate is not. That's our attention, our task, knowing what has gone into it, what is it that we're left with. So present in Dead Sea salt is as follows: all of these chlorides, sodium bromide and also magnesium sulfate with these percentages. Now the salt is entirely soluble at this 150 gram input amount, so if no reaction occurs, then these get taken out with the first wash. So anything here that doesn't react is gone, so we can eliminate all of these. Now these are the possible reactions that could occur. Some are known, others are not 100% known. For example, potassium hydroxide. However, if potassium hydroxide reaction does occur, then it is soluble in water at these amounts, so it would go with the first wash. Now sodium chloride, which is salt, obviously just carries straight through and out in the wash. Bromide, it's already sodium bromide and tide, and yes, it's soluble as well, as already stated. Calcium hydroxide, if that forms, then it's soluble at this amount. All of this you can just get off Wikipedia for that matter. And magnesium sulfate could form into magnesium hydroxide and also a sodium sulfate. So magnesium hydroxide is the same as this magnesium hydroxide and is not soluble at the first rinse, so would remain, but that is the next substance that we deal with. And yes, the sodium sulfate is also soluble in water. So what are we left with? Just magnesium hydroxide, and that's it. And when we come to the hydrochloric, all these get washed out, and then when we come to the to redissolving down to pH 1, then the magnesium hydroxide all goes back to magnesium chloride, and then as we begin to the precipitation, then we leave this in precipitation, is what we're saying. So provided it doesn't come out in any kind of precipitation up to 8.7, then it goes out with the first wash as well, which leaves us with nothing, or leaves us with X or M state elements. So there's still a bit of a question surrounding whether the precipitate is actually magnesium hydroxide, and we need to work on that next. But it's looking positive. So this is an overview of the experiment with an attempt to get a firm handle on what the first and second stage precipitate is, whether or not it's magnesium hydroxide. So this is an outline of it, of what you'll find in the rest of the video if you want to watch that. So starting off with 150 grams of Dead Sea salt dissolved in a litre or so of water, as my normal practice, and we're taking that to 10.7 pH, and we're taking a sample of that precipitate, which becomes sample 116A, and then proceed to reduce the wash and then reduce the precipitate pH to 1, whereupon it clears, and then back up to 8.7 slowly to produce the second stage precipitate, which is the normal Ormus that people would take. And so bringing sample 116A, which is the sample of the first stage precipitate, bringing it down, we're taking a sample of the second stage precipitate as well. And the rest of the precipitate will go into bulk storage as normal, and we'll proceed with the two samples. Now the two samples are then taken to pH 12 to take any M state into solution, thereby we're excluding the magnesium hydroxide, so any differences between the two samples should show up there, and the precipitate that remains, then we'll take that on and we'll do a further leaching of that and heat that to 75 degrees and take the solution off of that, and that solution should be a weaker solution of the racking that we did just prior to that. The precipitate is then taken on, and if I can move this across a bit, the precipitate is then taken on and dried, while the four resulting solutions are all taken down to pH 8.5 to do a re-precipitation of that solution, and back up to 10.7 to go through the magnesium hydroxide zone, and also to capture any platinum group elements there. Now the results were that in terms of this solution, then we produced a precipitate in the re-precipitation. Now it was a very much reduced amount of precipitate, and the precipitate that was dissolved at pH 12, it appeared that hardly any of it dissolved, yet some must have dissolved to produce that translucent precipitate that we got. Now this second lot of samples from the leaching produced no observed precipitate, so we didn't do anything further than that. So we have produced something. It is a different precipitate, and it is a smaller amount. My guess is that it's in the region of 3 to 5% of what we started with, and the precipitate itself that was taken off from the heated sample and dried, then we had something very unusual happen with that, in that the second stage precipitate, which is supposedly M state, did show a difference here. It's supposedly M state originally, that is, but it's supposedly magnesium hydroxide because it's excluded, yet it produced only 0.6 grams. It looked like it was the same amount, but on drying was only 0.6 grams, whereas the other sample was 2.76 grams. A big difference. So it looked like it was 85% of its mass was lost. So my overall conclusions from all of this data was that the second stage precipitate was mostly magnesium hydroxide, as a similar amount of first and second stage precipitate, when taken to pH 12 plus to exclude the magnesium, excluded a similar amount in both cases. So it had to be magnesium hydroxide, you would think. Secondly, and oddly, both samples ultimately yielded similar amounts of translucent precipitate, indicated that it is somehow associated with magnesium hydroxide, but it is no more concentrated in the second stage under the method that I used, which is all interesting. Thirdly, that the translucent precipitate is unlikely to be magnesium hydroxide, which you imagine it could be, we're just reducing the amount of it. And the reason for that is that the pH solution, which was heated on what we think is magnesium hydroxide, did not produce a precipitate. So you would think that if the first solution with pH 12 solution around it yielded a magnesium hydroxide solution precipitate, you'd think the second one would as well. So my conclusion is that the translucent precipitate is not magnesium hydroxide. Fourth, and also it would be unlikely to be silicon or anything like that, because heating it would be more likely to produce that that element in solution. So fourthly, there is something very odd about the second stage precipitate anyway, as after being retained above pH 12 it seemed to lose about 85% of its mass on drying. So there was some indication that it may have had a lower density, because when it was being heated it seemed to go cloudy, whereas the other one did not, and it also seemed to clear more slowly when it was stirred up. But almost certainly, even if this was the case, it was lower density, it's hardly going to account for the amount that we saw. So I can't account for it. I don't know what it is that we're missing, if it's something desirable and is now gone, why we didn't capture it, but it is an observation for somebody to consider. Well, that's it. Enjoy the video. The 3 washes are finished at 10.7. I could have continued to settle out a little bit longer, but it won't matter too much in this case. However, I will take off that last little bit of moisture, and a good way to do that is take a bit of regular kitchen towel and fold it and then roll it like this, and you'll find that if you just dip the end in that, you can use it as a wick and it will very quickly soak up. So it's already up like 30 millimeters, 40, 50 millimeters, 60. Cut it off like that, and you'll be able to draw a lot more that moisture off without sucking up the Ormus. I'll just do a little bit more. I'll just do this whole towel actually. It's very quick. I'm not worried about getting every last little bit, but in certain experiments it'll be important for you to know that technique if you get into this kind of stuff. Even with a syringe, you'll find this Ormus is so milky that it will draw up, but if you could look at this closely you'd see it's not going into the tissue. There we go. So now I'll get some of that Ormus out and put it aside. Now you might have noticed that I avoid using anything metal, because acids and bases and metal, and just introducing a variable into the equation. And also, people who are ingesting this stuff, it's important to keep everything away from metal. Apparently stainless steel is safe, but the stainless steel that you buy may not be safe. Now I probably don't need too much of this to compare at the next stage of the experiment, because as you know we don't get that much. Anyway, so I'll put that aside and I'll catch you when I've re-precipitated this. I know, very official looking, official engagement today. Ignore it. Well, we're on to the next stage. As you remember, I took a sample out at pH 10.7 and then took the rest of it here back on down to pH 1 and then back up to 8.7 to first of all dissolve it and then to re-precipitate, which that's been done, and you can possibly see that there. Now I've taken a sample out of that so that we've got roughly equal samples, and it does look a little bit more in that one, but the level's the same and it's taken at a similar stage in the precipitation, so I believe there's about the same amount of precipitate in each one, but I think that's going to be immaterial to the experiment in any case. Now, first differences, you'll notice there's a slightly different colour. That's normal. Then the first precipitate's normally very white, and this one's more of a tan colour, although upon powdering and annealing it does tend to lighten up, but that's for later experiments for you guys. Now the next stage will be to take both of these up to pH of 12. This one's already at 10.7 of course, so it won't need to go as far, but who knows how much will sodium hydroxide will be necessary to do that in each case. I will add a little bit extra water to that. Experience has showed me that you need to do that, otherwise you have trouble getting to that pH, something to do with the buffering. So apart from that, adding a little bit more water, it may end up being in a different container because the volumes will change. And if you ever want to do this, take a sample, then you just need a longer piece of hose on your trusty syringe. After all, I won't lose this precious precipitate. This one's not much worth to me because only a very small amount of this precious material in it. So I'll be able to re-precipitate whatever happens, and it will go along with this one into my store, which will start to answer what this material is. What do we expect to happen? I really don't know. I suspect much of this will not dissolve, and I suspect most of this will, if not all. And so then we'll be left with, what is it? As you can see, then A's on the left, B's on the right. I don't believe that's got rid of any of the precipitate. Remember, that was in quite a small sample jar, so it looks to me like it's pretty much all still there, and certainly our purpose is to split the two, see if there's a difference between the two. It's not showing anything. The colour, B is still slightly more tan than A, so I think that hasn't changed either. So my choices at this stage are to rack it off, and I've decided I will rack them off. That's what I'm doing now. And the solution I'll take back down to 8.5 and back up to 10.7 and see what I get between the two. That supposedly will be the dissolved M state, if any. And the precipitate, I'll add more pH 12 solution to that, perhaps in a smaller container, and bring them both to the, not so much to the boil, but heat them up and just observe whether any difference is between the two. Heating up by 60 degrees, then B had gone cloudy, but by 70 degrees it had roughly cleared up. You can probably see it stirring there, whereas A has remained clear all the way through. We're at about 75 degrees now on both of them. Let's see if I can lift this up and keep it in the frame. I'll just keep it at 75. I'll just stir them both up, and now I'll let them boil or simmer for another 5 minutes at 75. I'm about to turn off. Then you can see A is settling quickly, whereas B is not so. A and B have cooled down overnight, and what's immediately striking is that B has gone from the darker brown to almost a white, and you can't help but thinking if we had a heat treated another 5 or 10 minutes longer. I'll just play some light off that from my iPhone, you might get a better idea. That's very white. And as to volume, look, it may be that there's slightly less in B, so it may be that something's gone out of solution to allow it to become white. Also, the overall volume strikes me as being a little bit more. You might remember it was in that container in the left, and you would have been lucky if it was 40% of that, if we'd allowed it to settle properly. The two solutions have now been sitting at pH below 9 for a couple of days, and look, there's a very small amount of translucent precipitate. I think you can just grab it there. If I can get my other hand in the shot. Oh, here we go. Get my finger, where is my finger? There it is. Okay, just along here. Wow, what a fingernail. Just there. And you can see it a bit clearer there in sample B. So I think the goal will be to bring that up to pH 10.7. Now we shouldn't have any magnesium hydroxide to speak of in this sample, because that's what we left behind when we racked this off. We're just dealing with a solution and any dissolved supposed M state, so that's what we'll do. It's been sitting at 10.6 for a couple of days. Haven't really got any more in there. In fact, it's so transparent it's hard to see. I'll just see if I can reflect some light off it. Just want to show you real quick. You can probably just pick it up in the bottom there. So they're pretty much the same, and they look identical. So I've got so little of it, what I'm inclined to do is to rack them off into the same sample and try and compare this precipitate with the other one, and best hope of learning something from that. Precipitate, which has now been combined because they both looked identical and was about the same amount, and once dried, if we go that way, then it would be too small an amount on their own to compare. So I'll carry that forward and compare with the precipitate that's been that is still remaining from the beginning. The solution that was taken off that precipitate after it was boiled, or not so much boiled, but taken to 75 degrees C, was attempted to re-precipitate out of that, and we got nothing. So this middle line of inquiry shall just disappear from now. There was no more so-called M state in that sample, so that's it. Guys, this is really annoying if it's not exciting. Then, as you can see visually with the eye, then sample B, which is the second stage precipitate, dried to a significantly less amount. It's only 0.69 grams compared to 2.76 grams for the first stage precipitate. Now, you saw it with your own eyes. They look like a similar amount. You could possibly say that B was a little bit lighter, because remember when we heated it up in water, then it was more floaty, but I just wasn't expecting this. I could have done a volume and mass check and worked out from that something, but I didn't, and I really don't want to do it all over again. Anyway, I think I'll just proceed with my test to heat it up to 350 degrees C and see if we lose an expected amount of mass. Now, I did check the oil temperature, that I had this in my standard sort of oil bath method of drying it out, and the oil temperature was 170 degrees C, so it's nowhere near the 350 that would have, not that it would have counted for that much mass loss anyway, but I'll press on.